What's up, guys? So today we're going to be solving a 111 minimum depth of binary tree. This is one of the easier LeetCode questions when it comes to tree traversal. So let's get straight into how to solve this. All right, so first things first, we have to go ahead and find the minimum depth, meaning we have to go from the root node all the way to a given leaf node and making sure that we find the minimum depth. So for this problem, it would be starting here and then here. So it would be a depth of 1 and 2. Now, how would we go ahead and achieve this? Well, we can go ahead and do a simple BFS and stop as soon as we go ahead and find a leaf node, making sure to keep track of all the levels that we've went through. So for example, here we do 1 and then 2, and then we notice here that we reach a leaf node, meaning that it has no children nodes at all. And that's when we go ahead and stop and we return the number, which would be 2. So I'm going to quickly go over how our queue would look like. If you're comfortable with BFS, then you can go ahead and skip this part, but I won't take too long. So basically we're going to have a queue and we will have a level variable to just keep track of our levels. We're going to start off with 0 and our queue would start off with 3, the root node. Now again, you're going to pop this, and every time we go ahead and we traverse the entire queue, we update the level. So we're going to go ahead and traverse the entire queue, which is just 3. So that means we have to update this and do a +1. So it would be 1. And erase this, and we have to go ahead and add its left node, which is 9. And then its right node, 20. Great, we have 2 numbers right now. So again, we're going to go through the entire queue, and since we initialized the loop for the second line traversal, we'll go ahead and update this +1, making it 2. Great, and we go ahead and we check the number 9 first because it's a queue, and we notice right away this one has no children nodes, meaning it's a leaf node. So that means we go ahead and just return 2, and that's it. We end the program right away because there's no need of traveling to the other ones. We already have our solution. All right, guys, so let's go ahead and solve this. I've already initialized all the base stuff that we need. So I've imported deck from collections. I have set up our base case where we might not have any single root, like there's no tree at all. And our initial variables, I've initialized min depth to 1 already because we know that if we put the root inside, it's already 1. But without further ado, let's go ahead and implement this. So first things first is we need to go ahead and keep track of what level we are on. So we need to be able to know how many nodes are in the current level. Great, so this is how we're going to do it. Now we need to traverse the entire level. Okay, so at every single iteration of our for loop, every single time we start the for loop, we need to go ahead and increment our min depth variable. And we're going to do it at the end because we have already put it to 1. Great, so what do we do inside the for loop now? So we have to go ahead and check if we have a right or left child and add them. And we also need to be able to tell if we have a root node, and we also need to be able to tell if we have a child, and we also need to be able to tell if we have a leaf node. And the way we're going to go ahead and check this is if it has no children at all, then we go ahead and return immediately no matter what. Great, so it's really just as simple as that. We check if we have a right or left node, we add them, making sure to always add the left node first because that's how BFS works. And here is our condition to be able to tell if something's a leaf node. If it is, we return immediately. So let's just test this out if I've made any mistakes. Great, so I did make a mistake. We have to pop the node, so forgot about that. And there we go. Now let's see how well we do on space and time complexity. And there we go. We have amazing space complexity right here and amazing time complexity. I hope you guys found this useful. If you did, please leave a like and subscribe, and I'll see you in the next one.